Number 5, we've got a shop owner which is to hang a uniform 20 kilograms square. The length of the sign is 1 meter, so we've got over here, this sign is 1 meters long. We are told that the whole rod is 4 meters. The length from the rod to the string is 3 meters over here. And the mass of the sign here is 20 kilograms. Mass of the rod is 2 kilograms. The diagram, we can draw the diagram together with the dimensions and the forces that are acting. We've got the weight in the middle exactly, which is 2 kilograms. Instead of kilograms, I'm writing it down as the weight by doing mass times gravity. So this is going to be 2 times 9.81. Whenever I need the weight, I'll use 19.62. The sign has a mass of 20 kilograms. Multiply by 9.81, it becomes 196.2 newtons. The sign has a total length of 1 meters, so this will be 0.5 meters and this will be 0.5 meters. From here to here we've got 1 meter, from here to here we've got 1 meter, so we can see that also the distances to the pivot, because here we're going to have the pivot of rotation. Distance from this weight to the pivot is 2 meters. Distance of this weight to this pivot will be the whole 2 meters plus this 1 meter together with this 0.5 meters. So distance from here to here will actually be 3.5 meters. Here we've got the tension. Tension is at an angle also. It's an angle which we don't know, but we can calculate it because we need it. So I'll draw this triangle at the side. This length here is 4 meters and this length here is 3 meters. And from there we can get what is the angle here, which I've called alpha. We've got the opposite and adjacent, so I'm going to use tangent alpha. Opposite over adjacent, so tan alpha is 3 on 4. Alpha will be 36.9 degrees. So now in the diagram I'm going to insert 36.9 degrees because I found that angle. Again, I need components of the forces which are not vertical or horizontal. For the tension, I'll write down T sine 36.9, and to the left I've got T cos 36.9. This is the reaction at the wall. Also, I will need its components at one point in the problem, so I'll write down R sine theta, and here R cos theta. First part of the problem states the two conditions necessary for the system to be in static equilibrium. This one I've written it down already. To be in equilibrium, total forces in both directions must balance, meaning forces up equals forces down. And also, total clockwise moments must be equal to total anti-clockwise moments from the law of the moments. We call this the law of coplanar forces. Both forces and moments must balance if it is in equilibrium. Part B, we've got determine the tension in the cable to keep it in equilibrium. Here I will have to use the law of moments, take moments about the pivot. So I'll write down take moments about pivot or about the wall. Clockwise equals anti-clockwise moments. Clockwise moments will be this moment and this moment. So this force times this distance, which is 19.62 times 2. So we'll write it down in brackets because we've got another one. This also is clockwise 196.2, and this distance, as we said, it's 3.5 meters. and those are equal to the anticlockwise moment, which is this one, perpendicular distance of t sine 36.9 to the pivot is now going to be 4 meters, because that is acts from the end to the side. We've got 2, 1, 0.5 and 0.5, so that is times 4 meters. So anticlockwise moment is t sine 36.9 multiplied by 4. And once we get t subject of the formula, everything, we take it to the other side. First we add these together, and then you divide by 4 times sine 36.9, we'll get the value of the tension, which should be equal to 302 newtons. Next part, determine the magnitude and direction of reaction force at the hinge. So that means we're going to find what is R, also what is theta. Apart from moments, we can use the forces upwards and forces going downwards. So we can say that the forces going upwards equals forces going downwards. The forces going upwards are R sine theta this is going upwards together with t sine 36.9. So plus t sine 36.9. Instead of t, we can put 302 sine 36.9. And those are equal to the forces going downwards, which are this and this. So the forces going downwards are 19.62 plus 196.2. From there we can get r sine theta, subject of the formula. We've got 2 unknowns and 1 equation, so we cannot solve it for the moment. So if I work out this part, 302 sine 36.9, and I take it to the other side to become minus, we'll get r sine theta equals this value, 34.5. We can also look at the forces horizontally. R cos theta must be equal to t cos 36.9. So I'll write down r cos theta to the right equals t cos 36.9, and we also know that t is 302 as before, so we can work that out, and that works out to be 241.5. Now we've got 2 expressions, one in terms of r sine theta, one in terms of r cos theta. I'll write them down again now. R sine theta equals 34.5, r cos theta equals 241.5. We can divide. R will cancel. Sine on cosine is tangent theta. And this you divide it and work it out, and you'll get theta equals 8.1 degrees. Once you found theta, you can also find reaction R by using one of the equations. I would like to use r sine theta equals 34.5. So I'll write down r sine theta. We know that theta is 8.1, so r sine 8.1 equals 34.5. From there, I'll make r subject of the formula, 34.5 over sine 8.1, and that one should work out to be 244 newtons. Finally, explain why it's desirable to keep the cable attached to the rod furthest away from the hinge. This one is simple. All we have to say that is that the further the sine is away from the rod, the larger the distance, the smaller the force needed to keep it in equilibrium. Okay, so the larger the distance, remember that force moment is force times distance, the larger the distance from pivot, the smaller the force required to keep it in equilibrium. The larger the distance from the pivot, the smaller the force required to keep it in equilibrium.